reduce to matrix in a more or less block diagonal form, have to do special tricks, and it all depends on the application. But sparse computations for the current architecture, of course, are very inefficient. But again, if you can store the matrix, there's nothing else that can be done. So one remedy would be, for example, for a sparse matrix to multiply not by one vector, but 10 vectors. This would be more efficient than doing it sequentially, because you can load basically blocks, and this would be more efficient. But again, this is sort of tricks. Did I answer your question? Okay. So that's what you have already seen in your homework. The matrices that correspond to shifted variant structure. So it means that there are sort of regularity pattern in the matrix. In this case, the matrix has the same elements of the diagonal. And this class of matrices, Topliss matrices, is very important in signal processing. It's related to fast Fourier transform, and it's also well, this is an advanced specialized topic, but I have to mention it. So Topliss matrices, one-dimensional Topliss matrices corresponding to one-dimensional aperiodic convolutions, they form a subclass of so-called low displacement rank matrices, which is based in fact on low-rank matrices. Low-rank matrices are actually a very useful tool in many applications for representing structured matrices. So if you want to solve a linear system, a matrix is of course not of low rank, but we have a dense matrix which have very large low-rank blocks. So this is so-called block low-rank matrices. So, for example, you have a sparse matrix plus the matrix of low rank plus several matrices of low rank. And this is the third large class of matrices for which efficient numerical linear algebra algorithms can be used. They all start from fast matrix-directed product, but for some cases you can develop efficient factorizations. But in each of these cases, for sparse matrices, it's not trivial even to do Gaussian elimination in an optimal way. This is NP, whatever, hard and so on problem. For Topliss matrices, if it's a one-dimensional case, you only do one-dimensional convolution, it is possible to solve this problem to the optimal complexity. If you go from one-dimensional case to two-dimensional case, it is not possible to solve the problem for a general case, but for special classes you can do something. And in this case, there are quite a few algorithms that utilizes, so basically they approximate the inverse of a sparse matrix by a low-rank block or low-rank matrices. But this is all future, that's the plan, how we discuss. So the questions, we have a decomposition, how we compute particular decomposition, when this decomposition exists, does it exist for any matrix, so should be there some additional constraints, and what is done in sort of real life. So in real life, the answer is to use block algorithms to reduce the algorithm to the block version as much as possible, so we can really make use of efficient hardware. So the actual implementation of LU, of QR in this software, they are much more complicated than a simple, for example, LU can be implemented in 3 cycles, like 5 lines of code. But the actual algorithm is much more complicated. LU, Haletsky, quick reminder, QR, and sure. So LU is representation of the matrix permutation, lower triangular, upper triangular, and if we invert, we get this. So this is forward pass and backward pass given factorization. Factorization costs n cubed, but solution if you have factorization is n squared. And we do it using Gaussian elimination. If you have positive definite matrices, then every positive definite matrix can be factorized in the product R times R star. So we will need this fact for the existence of the QR decomposition. So when we will prove that QR decomposition exists for any matrix, we will use the Haletsky factorization. So LU, that we will cover QR. So when we are talking about LU can be defined in principle for the rectangular matrix. Then if for example, the matrix is tall, L would be also tall trapezoidal, which I cannot draw. Here I can write something here, but you will not be able to see. I got my stylus. So, okay. Yeah, so if you have a rectangular matrix, you can define a value with clear thing even to me. So its representation would be lower triangle here, lower. Yeah, that's and upper triangular. So this is also valid LU decomposition, but again, typically LU is used for solving linear systems with square matrices. So the application of this rectangular LU is not so straightforward. There is, but I don't want to discuss. But for QR, it exists for any matrix. So again, typically we talk about tall matrix. So talk about tall matrix. So the tall matrix here represented as a product of column orthogonal, right? So formally speaking, if you're talking about orthogonal matrix, it's a square matrix. So if you talk about unitary matrix, it's a square matrix. If you have the matrix with orthonormal columns, we either call it matrix with orthonormal columns or column orthonormal. Just, it's a good idea to be strict. If you take orthogonal matrix, in principle, it could not be rectangle. But here, when we are talking about QR factorization, where I mean, and the matrix is tall, it means that we have the matrix that has orthonormal columns. And then you have upper triangle here. So you have orthonormal columns and upper triangles. So what happens if you have, so this is so-called thin decomposition. There are other definitions of this. When you put additional vectors here, and then this matrix gets something here and 0 here. But that's the standard way. But changing options in NumPy enough, you can basically get different types of. So this is so-called economic form and so on. If you have a long matrix, then you get a square matrix here, and what is called trapezoidal matrix. So you have a matrix R that has zeros in the low, like you take a square matrix, you cut the corner, and then you cut the first row, so it's a trapezoidal form. This is also called QR factorization if you have a long matrix. So, yes, we have the poster for visualization. So, statement, QR decomposition, let's consider the tall matrix, but then QR decomposition exists for any matrix. We'll prove it shortly. But let's speak about applications. So one of the main meaning, or geometrical meaning of QR is that the columns, you have a column space. If you have a tall matrix, it means you have high dimensional vectors, m vectors living in n-dimensional space. And if m is equal to n, you have a tall matrix, it means we have probably 5 vectors living in a 100-dimensional space. And they form a linear subspace in the space, but they are not orthonormal. And the columns of Q, there will be also 5 columns of Q in this case, they will span the same subspace, right? And they will form an orthonormal basis in the subspace. So the meaning of Q, and Q is the most important part, that the columns of Q, they form the orthonormal basis. The fact that R is upper triangular in this setting is not so important, because, well, it basically says that we start from one vector and so on. So computing orthogonal bases. We have non-orthogonal vectors to compute QR, we leave the matrix Q as the orthogonal basis. Then it's used in the preprocessing step for SPD, but for example, if you have, again, a tall matrix, which is, say, millions times 5, if you do QR factorization, R will be 5 times 5. And Q is already orthogonal. Well, what it means, then you only need to compute SVD for a 5 times 5 matrix, which is much faster. So if you have Unbalanced matrix computing QR first reduces the computation of the SVD to a much smaller problem, which is very useful. But the third point is one of the most important. I already mentioned it several times. That would be near the end of this lecture, is the QR algorithm. Please do not mix QR decomposition with QR algorithm. Repeating it, we'll repeat it again and again, but we'll see. QR algorithm, this is substep. It's actually a very interesting and quite non-standard algorithm. I'm not claiming it's the best algorithm, right? So maybe you may come up with a better algorithm, but it's so even for classical algorithm, you do not have to take for granted that you have an algorithm which is the best. This is a nice algorithm discovered more than 50 years ago, which works nice, but if you look at the derivation, maybe you come up with a smarter idea. I don't know. Highly unlikely, but maybe. So it's based on the QR decomposition. And finally, if you have QR factorization of a tall matrix, you immediately get the solution of a least square problem with this matrix in the photo that we already discussed. So, that's the slide that shows how we compute the solution of a least square problem. Basically by taking QR factorization and then solve it, and then it's just equivalent to the solution of an upper triangle matrix, small one, with this. So the complexity is then computation of the QR. So this is just a reminder that you can do other ways. So even in this classical setup, if you have a classical setup of solving linear least squares problem, and people know how to do that for many years, there are actually algorithms that are faster. So if you have a really overdetermined system where the number of equations is much larger than the number of unknowns, there's well, I think the right way, writing it is a nightmare, but okay, Kaczmarz algorithm. So, and that's the example of, this is the example of more modern numerical linear algebra research. So numerical linear algebra is not like fixed carved in stone, so people still do something interesting. Not always, but yeah, maybe. So you have a system of equations, right? This one. And then what you want to do is you basically have the complexity that is proportional to the number to n. And if you have linear squares, in fact, n is equivalent to the number of samples. This is a least squares regression. And one of the ways we can do sort of stochastic method. So instead of considering all the equations, and each equation corresponds to a sample, we want to fit our data point to our unknown to the specific data point. In fact, you can use stochastic gradient descent for this very easily, but the convergence of stochastic gradient descent for this can be quite small. Instead, this method is fine in the sense what we do. So instead of solving one equations, we pick one equation randomly. But we had one previous, the one from the previous iteration. We had an example from the previous iteration of approximation. And this is also an example of an iterative method, but it's not a classical iterative method in the sense that the classical iterative method it uses matrix by vector product. Here, if n is very large, matrix by vector product is too expensive. We do not want even to spend we do not even want to multiply matrix by vector. What we want, we just take one row, and we find the next approximation as the closest one to the current, subject to some constraint. So this is a simple problem, and that's the solution. Well, if you look more closely, this is a stochastic gradient descent, but the step size is related to the norm of the row. It's very simple, you can implement it. But actually, the analysis of this is quite complicated. So the convergence analysis of this algorithm was done only in 2009, which is less than 10 years ago. And people are still working on how to speed up and so on. So this is a short, lyric thing. So even for a classical numerical linear algebra problem, if you put it in a specific setup, very large scale problem, you can come up, okay, this is the method from 1937, but doing it in the right way, people only learned recently, and still there is an improvement of how we're doing that. So even for a classical problem, in a special circumstances we could do better. And we also had a project in numerical linear algebra last year, where the guys, they looked at this as an iterative method and proposed a certain acceleration method for it. So basically, adding some parameters for the previous iteration in order to speed it up, and there was an improvement. So it was statistically significant improvement of the convergence compared to this approach. And yeah, so again, this is an example of a regression problem, and well, you probably know how to solve regression problem. Again, you write the loss function and you run the stochastic gradient descent. But if the method doesn't work well for solving linear least squares problem, I think it's not a very good method. And probably some of you are familiar with this other method. Again, if you have free time, try running other method on linear least squares regression. You will see that